everyone, and welcome back. My name is Mr. Cobalt, and in this video I'm going to be talking about high and low spin octahedral complexes, and we're going to be answering the question of how do you determine how many unpaired electrons you're going to have. This is going to depend on what kind of ligands you have bound to your metal ion, and it's going to depend on whether or not the metal ion is a D6 metal or not, meaning does it have 6 electrons in the D sublevel? And also with regard to the ligands, are they high field ligands or low energy, low field ligands? And that's going to determine whether or not the crystal field splitting energy is large or small. Okay. If the splitting is large, then you're not going to get unpaired electrons jumping up to higher energy levels because that energy level is going to be too large to go. So they're going to be better off just being paired, even though there is that repulsion force there. But if the splitting is small, then they're more likely to jump up to that higher energy level to be by themselves, and you'll have more electrons that are unpaired. So let's take a look at this. So here we have cobalt F6 complex, and so if we look at the ligand here, the fluoride ligand tends to be a low energy ligand. So if you look, fluorine is typically a weak field ligand, which means that if it's a weak field ligand, then the splitting is going to be small between the energy levels, and so you're more likely to have electrons jumping up. So we got 6 electrons. So normally you would have the electrons fill in, doubling up, right? So there's part of it, and then you have higher energy levels here. So you get the splitting of the d orbitals into different levels. And so if you have 6 electrons, you might have them filling up here one at a time according to Hund's rule, right? Spin up, spin up, spin up. But then you would pair them up again. But if the splitting here, the delta, the crystal field splitting energy, if that's large, then they're not going to jump up here and they're going to pair up, right? We got 6d electrons. But if the splitting here is small, then they're more likely to jump up and fill in the spaces up here. So if we think about that, in this case, the fluorine is considered a weak field energy, so that's going to be a small splitting, and so they're more likely to jump up to that higher level. So they're going to jump up here first, right? Now we have all 5 of them, but we have 1 electron, so the 1 is going to be paired up. So we would expect 4 unpaired electrons for this one. Here, this is high field ligands, the NO2 and the NH3. Those are high energy, high field ligands. So we would expect that the splitting is going to be large. And so this, again, we have cobalt, a 6d6 metal. So we're going to have 6 electrons, but in this case, if the splitting here is small, right? This was small for this one, but if the splitting here is large, so the splitting large, then what's going to happen is we'll follow Hund's rule. So we have 6 electrons, 1, spin up, spin up, spin up, that's 3. And then instead of jumping up and filling this in first, because the energy difference is too high, they're going to pair up here. 1, 2, 3, that's 6. So in this case, Here we would have no unpaired electrons, so we would not expect any magnetic properties for this this particular ion, this complex ion, but we would expect magnetic properties for this one because we have unpaired electrons. And so I hope this was helpful. If you enjoyed my videos, please like, share, subscribe, hit the notification bell, make a comment in the comment section. Thanks for joining me. I'll see you next time.